I was lucky enough to be here last year, and I was very excited to come back. I think this conference has been wonderful. I described last year's edition as one of the best first years of a conference I've ever attended, and I think that this one continues to live up to that legacy for sure. So thank you so much. It's been a wonderful couple days. I'm here to, if you remember from me last year I did no slides, and I had a similar problem, but my plan was to live code the whole time, and Portuguese keyboard layout is, let's just say, different than the American keyboard layout, and so it was very complicated. So this year I thought I would bring wonderful hand-drawn slides instead. So before I left, me and my partner worked and put together 53 mostly hand-drawn slides. I had 2 slides with assembly language on it, but now there's only 1, so it got a little less scary. But I'm here today to talk to you about what Rust can teach us about Ruby. And so that topic is a little bit broad, so let me get into what I mean. I sort of talked about this a little bit yesterday at the panel, if you were here. So one of the things about computers is that we're fundamentally dealing with abstractions. And the reason I said one of the things we're dealing about computers is because actually everything that we're dealing with is an abstraction all the time. And so, in order to make that a little easier for you, I used the sentence computers to indicate that we're only talking about a certain subset of those abstractions. And we just do this everywhere with everything. And so we talked a little bit about how different programming languages have different models for abstractions, but like everything we do is abstraction all the time. So sometimes I hear people say things like, X is an anti-abstraction programming language, and that makes me think like you don't really know what abstractions mean, because even in the, this presentation is an abstraction. I'm taking some particular neurons that are firing in my brain, and then I'm creating an abstraction out of them that we call the English language. It's a very leaky, broken abstraction, and you all are receiving that particular abstraction, and then you transform it into your own internal representation, and hopefully it's not gibberish through that complicated process. And so this is true of human languages as well as of computer languages. And so, yeah, they're just abstractions for all of us, like it's turtles all the way down. You can't actually get away from abstraction. And one of the other funny, weird things about abstraction is we talk about this classic story of there are turtles infinitely up and down, but abstractions aren't as neat as a single line of abstractions going up and down. And you see this sort of, when we talk about these things in computer terms, we often talk about low-level and high-level programming languages, and I wish that it was that easy, but it's not actually that easy. So for example, abstractions can diverge and divide from one another. So if I have a Ruby program, and I want to think about how it works at a lower level, I can either go down the route of here is the Ruby interpreter, and then it produces some assembly code, and then that assembly code gets turned into machine code, and that machine code gets turned into microcode, and that microcode gets turned into instructions in the processor, and those instructions turn into physical actions of the processor, and then those physical actions are the result of certain laws of physics, and then you keep going down until we sort of go, yeah, I don't know how that actually works. Once you get to the subatomic particle level, we're like, but you can also take a Ruby program and say, okay, this represents an abstract model of computation that actually goes through lambda calculus and the Church-Howard correspondence, Curry-Howard, not Church, Church encoding, Curry-Howard correspondence. God, we invent a lot of terms in our discipline. But you can then go, instead of to the physical level, you can go to the other direction of here is the abstract way we compute stuff with Turing machines and just completely ignore the actual physical reality of the machine altogether. And so those two, to go down to the base level of the abstraction are completely divergent from one another. Like the abstract lambda calculus and Turing machines and the silicon that your computer is implemented on are very, very different, but you can reasonably get to both of those destinations from the same starting place. This is why computers are hard. One of the reasons why computers are hard. And so this is a quote that one of my professors said to me in college, and it's one of the things that stuck with me the most. And he said, operating system's job is basically to lie to you. So one of the things I really like doing to people who try to look smarter than other people by saying that they know too many things is they'll be like, oh, well, actually, this memory address is at this particular location. And it's like, well, your operating system is telling your program that it's at that memory location, but virtual memory means it could be anywhere inside the computer. your program running in a process inside of an operating system, again, this is not inherent to the way that operating systems are developed, and early operating systems didn't do this, but essentially any operating system that you're probably using today uses virtual memory. And what that means is your computer program is deluded into believing that it is the only piece of software running on that computer. And there's a very complicated set of abstractions that your operating system uses to sort of juggle behind the machine to make this lie appear true. So, it's not just that we're not programming at the level of the machine, but like literally your program does not realize that there are other programs running, which is kind of intense. And it's so funny because I am just old enough that I can remember when that was a new feature. And so there was this piece, little like 10-year-old me using his Mac, there was this new piece of software came out that I saw ads for in computer magazines. Those are like iPads in physical form. In there were advertisements for this program called RAM Doubler. And they were like, you can install this program and it doubles the amount of RAM you have. And little nerdy computer me was like, that doesn't even make any sense because RAM is physical hardware. And then years later, I went to my operating systems class and I was like, oh, it was a virtual memory implementation. So anyway, computers are hard. And they just lie to you constantly. So this is something that I always kind of remembered because it struck me as being very profound. But it's also just kind of true that no matter what you're doing, you're lying. Computers are so complicated now that assembly language is not actually what your computer runs directly anymore. The processor actually implements assembly language in its own abstraction, and so you program in microcode, which is lower than machine code now. So if anybody tells you they do the lowest level programming, they're probably lying to you. And so what do we do with this knowledge and this information? One of the things that you can do to get better at programming is learn other programming languages because they teach you other models of abstraction. And we can simplify in a certain context and say, OK, I know that this is a lie, but we're going to pretend like this is true because I have to get some work done at some point in time and not just sit and think about how everything is a lie. And so one of the things that you can do is say, all right, I have an intuition for how this abstraction works, and then use that intuition to get actual work done. So for example, I've never really needed to worry about Ruby internals to literally write my program before, but if I know a little bit about how Ruby works, then I can use the intuition that I've developed from that to determine, is this Ruby code going to be slower than that Ruby code? And furthermore, that's what I think is useful about learning other programming languages is they can help you develop intuitions for different kinds of computation, and learning more about the way that your program language works can help you develop intuitions for how your program will eventually run. And so, because everything is a lie, I am also going to be lying to you, but I'm trying to give you useful lies that you can use in your own work. And so with that, I need to apologize to Koichi. I realized that while I'm about to give you a high-level abstract version of the way that Ruby processes things, again, that's a lie, and I have the person who wrote it was going to be in the audience. So sorry that I'm about to misrepresent a little bit of your work. I hope it's not terrible. Also, my handwriting in Japanese is horrible. That sa, man, it's horrible. OK. If you want to know more at a lower level, I really, really can't recommend this book enough, Ruby Under a Microscope. It is awesome, and it's a really great way to get your toes wet in the ocean that is MRI and the way that it's implemented. One or two of the charts that I'm about to show you are basically transliterated from the book because I was like, oh man, I'm going to have to dive through the source to find out exactly how this algorithm works. And then I was like, wait a minute, Ruby Under a Microscope probably has a chart for this, and they did. So please read this book. It's wonderful. OK. This is a thing that we say in Ruby world, and it's true, that Ruby is quote-unquote slow. But we love it anyway. It doesn't actually matter that on the scale of most programming languages, Ruby is slower than other ones, because Matt's made Ruby to make programmers happy. And speed can make programmers happy sometimes, but there are other things that make programmers more happy. And so we kind of are just OK with the fact that Ruby is usually one of the slower programming languages, and that's not something that usually bothers us. And so for the rest of this talk, I'm sort of going to talk a little bit about why Ruby is slow, but also what benefit that gives us. Because Ruby is slow for a good reason, several good reasons, actually. And usually it's fast enough because computers are getting faster all the time. And so, like there are tons, even though Ruby is quote unquote slow, like you all make a living, or most of you make a living by writing Ruby code, so it's still useful. Okay, so why is Ruby slow, and like what does that actually get us? So when you actually write some code, there are a number of things that your programming language will do to take that code and operate on it in some fashion. And so the basic pipeline of the way that MRI works today is it takes your code, and then there's a tokenizing step. And I'm about to explain this to you in a little more depth, so I'm going to do the overview, and then I'm going to cover each step individually. So it takes your code, it tokenizes your code, and then it parses your code. And then, so MRI, as of 1.9, compiles your code. I'll get into that in a minute. And then finally, it runs your code, that compiled code, inside of MRI. Before Ruby 1.9, that compile step didn't exist, and Ruby was even slower than it is now. So the big difference between 1.8 and 1.9, at least in my mind, is that extra compile step. Okay, and so what are those steps? If you're not used to compiler theory, if you haven't dealt with that before, here's sort of what those steps do individually. So 2 + 2 is a valid Ruby program that computes the answer, 4, hopefully. And so you write down 2 + 2 as Ruby code, and then what it does is to tokenize that Ruby code, Ruby steps through your source code, and it says, OK, I'm going to turn this into a sequence of tokens. So Ruby understands, all right, we have an integer, and then an operation that's a plus, and then another integer. And then it takes that representation, and it parses it into a parse tree. So now we have this operator that needs 2 values, and those 2 values happen to be those integers, and that's 2 + 2. And so these are, again, the first kind of steps. MRI originally just operated on that parse tree, but now we have this compile step. And so if you compile, the compile step ends up spitting out this instead. So this is MRI bytecode. You can get it with the, there's actually a VM object inside of Ruby that you can say, please pass me this particular string of Ruby code, and then disassemble it into MRI bytecode. And so this is the bytecode for 2 + 2. So you can see that there's put object 2, and then a plus operation, and then leave to exit. So what your code is actually executing has almost nothing to do, quote unquote, with the actual Ruby code that you wrote. Koichi's talk yesterday kind of demonstrated this, right? Like those speed-ups that we're able to gain by making Ruby faster are for doing the steps. All those intermediate steps can be done in more efficient ways if you are smart and tricky and you know how to mess with those kinds of things. But like the code we type in is actually only tangentially related to the code that actually runs on the machine. So I have a sequence of slides. Since I said what can Rust teach us about Ruby, I'm going to show you some Ruby code and some Rust code and talk about how they're different from one another. So Ruby's computation model that I just showed you, when you type Ruby whatever.rb, it does the tokenizing, the parsing, the compilation, and then the execution. That particular model is one way of executing programs. But if we try a different programming language, that different programming language will have a different programming model, and that different programming model means that you can represent that program in different ways, and that can lead to a totally different outcome in the way that your code is actually run on the machine, and have wildly different performance characteristics. In this case, I'm just using performance because it's something that Rust is good at, but you can look at various different ways that your code can run and say, like, okay, even if I write the same code in 2 languages, why do they operate differently? And that's because they have different models of computation. So with Rust, side note, so that's the unofficial Rust mascot. Its name is Ferrous, which I think is hilarious because F-E-R-R-I-S is like a name, but F-E-O-U-R, I can't spell. But there's like, it sounds like a metal, like an iron as ferrous. Anyway, we say Rustation. Piotr mentioned this in his talk yesterday, so we describe ourselves as Rustations instead of, Rubyist is to Rustation. Rust's model is a little bit different. Rust uses an ahead-of-time compiled model And what that means is, instead of saying ruby foo.rb, where it executes all those steps at once, we say rustc foo.rs. And also, you'll notice I added the st on top of the ruby, because I've been joking that I'm only programming in languages that start with ru from now on. Like, that's it. Like, it's got to be, Ruby and Rust are both almost the same thing. So rustc foo.rs produces a binary that you can then run. And what that means is Rust uses those same steps of like tokenizing, parsing, compiling, but Ruby, because we want you to run one command and we want you to be able to distribute source code, it does all those steps every time you run a program. But when you make a Rust program, you compile it ahead of time and you do all those 3 steps once, and then every time you run it, you only do the last step. And so even just that most basic model of compilation or of computation can change your performance significantly. Python has a way of doing these kinds of things, and I know that Rubinius did, and I don't think that there was some discussion about bringing this idea to MRI of like you can save pre-compiled Ruby files and execute them directly. So another thing I want to stress is that often these are implementation details of particular implementations. It's not an inherent limit to the language. So like, if we thought that this was a significant benefit to Ruby, we could also follow this model in Ruby. But by doing all that analysis up front instead of at runtime, our programs can get much, much faster. So the first thing I want to do is talk about Ruby method lookup. And this is one of the most important things that you can learn if you're trying to go from a beginner to an intermediate Rubyist. I often recommend that people read the book Metaprogramming Ruby, which I believe has a new edition that just came out. And even if you're not doing any metaprogramming, in order to write programs that write programs, you have to understand how programs work. And so learning metaprogramming will make you better at understanding Ruby internals and just the computation model of Ruby, generally speaking. And so calling a method in Ruby is actually a very complex operation. Here's the chart. So you set the current class. If I have foo.bar and I need to look up how to call that method, naively speaking, you have to set the current class to be the receiver, and then you look through the method lookup table in that particular class, and you see if that method name is there. If it's not there, then you set the current class to the superclass of your current class. Fun trivia is that even classes are classes in Ruby. I love that aspect. It's ridiculous. And then you do that again, and you look through the method table of the superclass, and if it's not there, you look for its superclass, and if it's not there, you look through its superclass. And when you're writing your Ruby code, you're like, oh, that's maybe 1 or 2 things. Last time I looked at an active record model, its ancestor chain had like 25 superclasses, 3 of which were anonymous classes that it was mixing in. So sometimes this can take a while. But you look through all those things, and then eventually, if you find the method, you can call it. So this is the basic process by which Ruby works. Again, everything's an abstraction, so we can actually do some things ahead of time to make this faster, and MRI does do some things to optimize this when it can, but in the general case, you can't. So that's Ruby. Here's some Ruby code that is a method foo that takes 1 argument x, and it returns a 5 every time. And then we call foo of 10. So Ruby has to do that lookup, and in this case it's easy because there's only 1 level and we're not actually looping through superclasses, but in order to call this method, that algorithm or something like it has to be executed. So let's talk about some Rust code. Here is some Rust code that does the exact same thing as that Ruby code. I have a method or a function foo. It takes 1 argument called x that's a 32-bit integer, and it returns a 32-bit integer 5 every time. And we call foo of 10. You notice some things about this Rust code. For example, we have to annotate the types of the function. So we have to say that x is a 32-bit integer, and then it's returning a 32-bit integer. Rust actually has a main function. It just doesn't execute all of the code in order. So there's a little bit more ceremony. There's a little bit more stuff you have to do as a programmer to write Rust code. However, this is the assembly code that function compiles to in Rust. So that complicated algorithm that Ruby has to run as an interpreter to execute that call, this is the assembly. So if you're not super familiar with assembly code, which I assume most Rubyists aren't, this is basically like just putting a 10 into the argument register, calling the foo function, which itself puts a 5 into the return register. It's got this thing with 61. I'm not sure what that is actually off the top of my head. And then it returns back, and then it moves the return value back out and returns from main. So this is pretty fast. Like it fits on a slide. And so that is sort of the advantage of this particular model, is we're able to do a whole lot of stuff, and instead of having this algorithm, it's instead 20 assembly instructions. So that's calling a regular old function, a plain function. Now I'm going to show you something slightly more complicated, but not a whole lot more complicated. We're going to make this a class method instead. So here's a foo method with a hello, or a foo class with a hello method. It returns hello as a string. We make a new foo, and we call hello. So in order to execute this, again, MRI has to define all this stuff. It has to parse this all in. It makes it up. It does the method lookup. It calls all the receiver stuff. I'll show you the Rust code that corresponds with this Ruby foo. Again, there's some more ceremony. So we have to actually declare our behavior and data separate. So where Ruby gives you a class where you define attributes and methods, in Rust, you use a struct to define your data, and then an impl block for implementation to implement your behavior. So here we have no data, so we have an empty struct. We define methods calling hello, and again with these types. So Rust is a little more like Python in this way, that instead of an implicit self like Ruby has, it has an explicit self. So we have self as an argument, and then it returns a string, and we return hello, let f equals foo, foo.hello, and that's kind of the same thing. So this basically does the same thing as the Ruby code does. And again, due to the ahead-of-time compilation model and all of the static analysis that we're able to do and the type system stuff, this generates 82 lines of assembly. I was going to put it on the screen, but that's even less, useful if you're not like into assembly code. Showing you a bunch of it is not meaningful. But then, so I did this demo, and I was coding up this example, and I was like, wow, this assembly is really readable. And then I went, wait a minute, I didn't compile it with any optimizations on. And so there's this thing that you can do with ahead-of-time compiled languages, and you can do this with Ruby as well, of course, any language, but Rust uses them very aggressively. You can basically say, I would like to take a little more time when building my program, and I would like you to figure out and optimize as much as possible about it. And so Rust, in particular, is actually slower than Ruby without optimizations in many instances, because we just generate really crappy code. But when you turn optimizations on, it's sometimes faster than C. So like these things make a vast amount of difference. And in this case, it goes down from 82 instructions to 30 assembly instructions. And what's fun about that is if you actually look through those 30 instructions, it just says main return. Like the actual implementation, it figures out that, hey, this program doesn't actually do anything with the return value of foo, so we can just eliminate it. And then if you're not calling the method, you don't have to use the struct, so we can eliminate the struct. And then, since we don't use that struct anywhere now, or those methods anymore, we don't have to generate code for those either. And so basically, this is equivalent to a blank program, and so Rust's compiler spits out essentially a blank program, which is kind of cool, but also bad when you're trying to test how fast your code is, and then you write some benchmarking code that accidentally optimizes out to nothing, and you're like, my code is infinitely fast. Something must be wrong. So this kind of like ahead-of-time model, plus the type annotations and all this stuff, like lets you really, really aggressively optimize, which is really cool. I have one more example that I'm going to show you here of some Ruby code and then some Rust code. Here is the next level up is like we make a bar module with our hello function. We mix that bar module into our foo class, and then we call hello this way. So this will do like one of those lookups through that algorithm to find this class. And this dynamism and this metaprogramming is what really drew me to Ruby in the first place. Like I love this stuff. Like it's my favorite. The kind of all that stuff that Sam was talking about that's like actually kind of terrifying is like also kind of awesome. Like, sometimes you're just like, I really need to do all that ridiculous metaprogramming for fun because you're a terribly broken human being. And so here's the Rust code that's the same. So Rust has this thing called traits. And traits are sort of similar to Ruby modules in that they're a list of function types, and then you can implement that type by, instead of including a module, you implement a trait for the type. So here we have a struct foo, a trait bar that is a hello function, and we just give the function signature, and then we implement bar for foo by defining the body of this function, and then when I call foo and h.hello, I can still get that. And so this ends up being the same thing, and it's kind of the same model, but there are some significant differences. And this only looks the same as Ruby because this is the same case, so I'm going to show you a little bit of how this gets a little more complicated after showing you this Ruby function. So you wouldn't write Ruby like this, obviously, but for the purposes of demonstrating this particular feature, again, everything's an abstraction, right? So I'm going to show you some demo code, and demo code is always trivial because real code would take longer than 30 minutes to explain, and you really probably would get bored if I was showing you like, okay, here's 200 lines of code, please read your printouts. I've passed a copy out to all of you. We're going to be talking about line 72 through 65, and that just gets bad. So bear with me, this is clearly bad Ruby code. But when we write code in Ruby, when we pass an argument to a function, we just kind of assume that we know what types are getting passed in, right? So this morning, you saw that comment made by that particular committer to the Rails project, who left a comment saying that this argument will always be a string. And it turns out it's just not. And because Ruby is so flexible, we just accept whatever. It doesn't matter what object comes in. That's totally fine, because even method missing is still technically a method, and since you're sending messages to an object can always respond to any message you pass in, so it doesn't really matter, kind of. And so if I passed something into this function, it would still work. It would just throw an exception if it didn't have the appropriate method. You get a no method error. But in a language with ahead of time compiled stuff, like Rust, it looks a little more complicated. So this particular annotation says hello is a function that's generic over some type T. And by the way, that type T implements that bar trait that we talked about before. And then it takes one parameter, f, that has that type T, and I call f.hello. And then in main, I do let f equals foo and hello of f. And so now this also works. But you've noticed, again, I've had to explicitly state up front that there's some sort of interface that defines this particular function. And if the bar trait didn't implement the foo function, I would get a compile time error saying like, hey, T does not have any methods on it named foo. This doesn't work. Now, what's cool about this is that, like in Ruby, how you can mix a module into any number of functions, in Rust, you can implement a trait for any number of types. So here, I now have a quux. I never know how to pronounce that one. Those things are called metasyntactic variables, by the way. It's really interesting. We don't know where these came from, really. Like, the foobar thing is like a military term that some people say that's what it is, but it's actually really unclear how these things appeared. And so I've implemented it for both of these two types, and then I wrote my hello function as usual, and now I can call hello on foo and on this other class. And so that just works the same way that you would be in Ruby, and that's cool. However, what's interesting about the fact that we've had to define this stuff up front means that the compiler can do interesting things by actually analyzing what types we've passed into this particular function. So we call this monomorphization. This is actually really cool. It's one of my favorite words, mostly because it sounds complicated, but it's actually very simple. So mono means one, and morph means form, right? So monomorphization is turning things into a single form. So what happens is, when I write this hello is generic over a T that implements bar, when I compile this code, Rust turns it into, and it says, OK, what types did I call this function with? I called it with foo, and I called it with the other class. So I'm going to make a specialized version that's not generic called foo bar and foo quux. And then I'm going to replace the calls down below with calls to those special functions. So now, instead of having to do that method lookup chain by looking up through all of the ancestor classes, it's just like calling a regular function back to those 20 lines of assembly. And so while we write code that looks like Ruby, we get stuff that is way faster in this particular instance. And that's due to a little bit of burden of typing and typing in these types, but that means that the compiler can reason a lot about our code, which is really cool. And so we get back to those 30 lines of assembly. And so the thing that I want to point out here is sort of two things. First of all, I'm not saying that Rust is super fast and therefore you should throw away Ruby and use it. There are things that you can do in Ruby that you cannot do in Rust because of that lack of flexibility. So for example, all that stuff that Sam showed you is basically not really possible in Rust, basically. One might argue that that's a good thing, maybe, but I won't necessarily say that's a good argument. But also, it helps us by learning about these other languages. Like if you learn about the way that Rust does this, you might have heard about the optional type annotations that Mats wants to add to the next versions of Ruby. And so those type annotations would allow Ruby to do those same kind of optimizations that Rust does. And so if you were interested in the future of Ruby, you might be better prepared to understand those feature requests and like why they're wanted and the kind of advantage that you might get by adding optional typing to Ruby if you had learned Rust in the past. So this is kind of what I'm saying, is that like learning other languages can even help you, even if you don't use them in your day-to-day life, because you can sort of steal what's good. I've been kind of like joking by going around to different programming language communities in general that like I'm just trying to take everybody's good ideas and bring them back to Ruby. And I'm sort of doing the same thing with Rust. When we were working on Rust, we were using makefiles because C++ programmers use makefiles, and makefiles are terrible. I like them, but I also... So if I'm not using a makefile, I think make is wonderful. As soon as I start using a makefile, I'm like, why did I ever say I wanted to use a makefile? And so Yehuda and I campaigned really hard in the Rust world, and we said, we don't want to use makefiles. We're going to build this tool and call it Cargo. And it's basically Bundler. And the existing people were like, oh, that sounds kind of cute, but we're just going to stick with our makefiles because that won't really work. And then when we built it, they were like, oh my gosh, this is amazing. So I've been trying to take Ruby's good ideas and put them into Rust. So I think it's only fair that Ruby takes Rust's good ideas and puts them into Ruby, because that's how we all get better, is by sharing our experiences and understanding what's going on. So Ruby offers us a great deal of flexibility, and Rust offers us a great deal of performance. And depending on what you're doing, that should be the way that you choose the language that you pick for any given project, even if it's more than just Rust and Ruby. All programming languages have some sort of advantage, because that's why the person made the language in the first place, right? Like, if nobody goes to make a new programming language and says, yeah, there are other languages that do everything mine does better, but I'm just making mine kind of crappy because I don't know. Right? Like every language designer is like, no, there's something that makes my language special. There's something that makes it better. And so they're all valid for different use cases, and they should cross-pollinate as much as possible. And so if you like to say, like, I'm a Rubyist, and therefore X programming language is stupid, or I program in Rust, and therefore X language is stupid, I'm here to tell you that all programming languages are cool in their own way, and so you better just deal with it. So I wanted to take the turtles and make them fast, so I added little speed markers, but it kind of looks like they're farting. And I was like, do I want to fix it to make it more clear? No, I think I would rather just make them look that way. I like the ambiguity of that aspect. So that is what Rust can teach us about Ruby. Thank you again so much for having me, and I have no idea if I have question time or not. So thank you.